Next, we have Ryosuke Okuno from UT Austin to give us a talk about novel fluids for enhanced carbon storage.
All right. Thank you so much for the introduction. Hello, everyone. I'm Ryosuke Okuno from the University of Texas at Austin. So this is the first time for us to attend this Energy Simulation Summit, and we are very much excited. And thank you for the opportunity to share some topics under our consortium at UT Austin. So we have the consortium on carbon utilization and storage that is called red. Okay. So it's called Carbon UT, and this covers a range of topics in carbon hydrogen space that include CO2 capture, CO2 conversion into different products, EOR, CCS, and some hydrogen related topics. So for the CO2 capture process, we are looking at the optimum formulation and particularly surfactant additive to the amine solution so that we can selectively increase the bicarbonate concentration while capturing the CO2 in the media. And for the CO2 conversion topic, we are looking at the different products such as formate, formic acid, syngas, and methanol, and they are through electrochemical reaction. And one of our postdoc fellow, Omar, who is in the audience today, so he's going to have a poster on CO2 capture topic. And his main focus is actually in the second topic on electrochemical process, but update will be given in the future. And EOR and enhanced carbon storage. So we have two main topics on enhanced carbon storage. So first one here is aqueous formate solution. So we are proposing to use a formate as a carbon carrier that can dissolve in water, so we can make a carbon bearing water to inject the carbon into the formation as water flooding. And the second idea here is to make a nanobubble dispersion of CO2 in the water. So this is another way to transport and store CO2 in the aqueous phase. And we were able to, just recently, we were able to make a stable nanobubble dispersion of CO2 in brines. And today I'm going to discuss some details of aqueous formate solution topic. And here you can also see CO2 storage in tight formation. So we have Sofian in the audience. So he's one of our PhD students working on this topic, and he has a poster on this, the tight formation transport phenomena. And lastly, we have the hydrogen related topic. So we are looking at the formate of formic acid as a hydrogen carrier for geological carbon storage of hydrogen and transport and delivery to hydrogen fuel cell. So I'm going to start by this schematic of carbon balance in oil production and carbon storage. So carbon balance here means carbon out and the carbon in through the boundary of surface and subsurface here. So CO2 generated from different industrial processes are captured and are compressed because it has to keep high carbon density for transportation purpose, and injected into the formation for carbon sequestration and enhanced oil recovery. Now C, this letter C in CCUS stands for actually carbon, not CO2. So the question we had at the beginning of the program was, okay, what other carbon species we can use for enhanced carbon storage compared to CO2? So this question came because it's not the easy task to make this carbon balance in oil production and the CO2 storage process. So here I'm showing a carbon density of oil. So here I'm using pentane as the example oil on the left-hand side and the CO2 carbon density on the right-hand side. So suppose we have a formation pressure temperature that are 10 megapascal and 75 degrees Celsius. The production of 1 liter of oil results in 40 mole of CO2 emission. And if we use the CO2 as a carbon carrier and store the carbon as a CO2 in the same pore space of 1 liter, that pore space can contain only 5 mole of CO2. So it's not easy task to make a carbon balance using a CO2. So we increase pressure, or we store CO2 in a deep formation so that the density of CO2 is high. However, the density of CO2 is not, it's much smaller than liquids such as formation water and oil. So that results in buoyancy driven upward flux of CO2 that lead to potential leak of CO2 to the surface. And also CO2 displacement of water is not efficient because it's immiscible multi-phase flow displacement with a very small viscosity compared to the water to be displaced. So all these factors collectively reduce the efficiency of pore space utilization by CO2. So we look at the different species, and we are particularly interested in this formate, which is a conjugate base of formic acid. And the formic acid is widely studied as a hydrogen carrier, and we are looking at the formate for geological applications. So in a typical formation pH environment, formate is a species. And then when pH is smaller, like a 2, then it's a formic acid. The formate is very stable, and we are proposing this as a hydrogen carrier, carbon carrier that dissolves in water. And also I'm going to show later, this viscosifies the solution, so it can stabilize the displacement fronts. And the formate by itself can be hydrogen carrier and also raw material for different carbon species. So the conversion of captured CO2 into formate or formic acid can be done by electrochemical reaction. And this technology is currently rated as TRL 6. So using a formate, the previous schematic can be modified this way. So first we are doing R&D for integrated system of CO2 capture and reduction into different species. So for the surface application, we are particularly interested in formate. And if this process is done by renewable energies, the proton taken from the water to make a formate is a green hydrogen, basically. And the FM stands for formate, that dissolve in water at high concentration. So we don't have to use a gaseous species for this process from this point on. So no CO2 from that capturing point. And transported using aqueous phase and injected just like a water flooding. And carbon sequestration, EOR, and the storage of renewable energy are possible with a formate. And using this integrated system of CO2 conversion, capture and conversion, we can come up with some hypothetical value chain of hydrogen. So here I'm listing, showing FA stands for formic acid. It can be transported to a location of hydrogen consumption, and dehydrogenation resulting in hydrogen gas. This can be at a very high pressure for hydrogen fuel cell, and that also gives us CO2. And this CO2 can be converted back to formic acid using renewable energy, using the same process. And you can find a local generation consumption process of hydrogen. So in this consortium, we are studying this integrated system of CO2 capture, reduction, and also surface processes in a box as part of the program. So I'm going to focus on subsurface application formate. We look at the formate because it's highly soluble in water, so we can make a carbon-bearing water with high carbon density. So here I'm showing a snapshot of a solubility test of formate in this case, DI water at room temperature, but we tested at the different conditions. So in this particular case, the solubility is 9 mole per liter. It's equivalent to 30 weight percent. And below 9 mole per liter, you see clear water. And beyond that, you see undissolved sodium formate at the bottom. And this clear water is actually more viscous than original water, as I'm going to show later. And at the wide range of conditions, we confirm the solubility of formate is ranging from 9 to 11 mole per liter, corresponding to 30 to 35 weight percent. And this is an enhancement of CO2 solubility in water by a factor between 250 to 300. So we can enhance the carbon density even at the low pressure. So here is one example of viscosity of formate solution with 49,000 ppm NaCl. So vertical axis log of viscosity, and the horizontal is molar concentration formate. So at the room temperature, 25 degrees Celsius, near the solubility limit, viscosity goes more than 10 centipores. And at 75 degrees C, certainly decrease with the temperature, but it's 4 to 5 centipores near the solubility limit. So I'm showing here the potential application for formate solution. So first one is EOR. So as you saw in the previous slide, we can increase viscosity so we can stabilize front of displacements for both oil and water in CCS/EOR. And in separate publications, we presented the wettability alteration by formate solution for carbonate. So it has a mechanism of EOR in carbonates by wettability alteration to enhance water imbibition. And using a formate as part of, say, WAG, we can decrease the carbon intensity of the process also. And for the enhanced carbon storage, as you saw in the previous slides, we can keep a high carbon density even at the low pressure. And before injection, we can adjust the density of injection brine. So we can basically control the buoyancy force in the formation. And the displacement of water should be very efficient in efficient CCS, and using formate, the displacement of formation water is a miscible process with a good viscosity ratio. So this is a significant advantage over CO2. And using formate, we don't need a CO2 pipeline transportation, gas compressor, and the recycling facilities. So we can save a lot of cost on these items, and then we can invest on reaction process to get the formate from captured CO2. So to show the subsurface flow regimes of formate solution process, I'm going to show simulation case studies. So the case was taken from SP10. That is very heterogeneous model with fracture networks. And initial and the production well pressures are 1500 psia. And for the CO2 case, to be compared with the formate case, the MMP is 1460 psi. So CO2 case is said to be miscible process. And we use the synergy gem with the Penn-Robinson equation of state. And we assume 5 years of water flooding followed by EOR/C carbon storage using either CO2 or formate solution. And the formate case has a viscosity of 5 centipores at the 30 weight percent. And we assume constant CO2 rate of 5 tons per day for the Q5 spot. And the main difference between the two cases come from the endpoint mobility ratio. So the injectant is displacing oil and water, and the endpoint mobility is very important. So CO2 case has an endpoint mobility ratio of 13 for oil displacement and 3 for water displacement. So they are not stable. With the formate solution, the endpoint mobility ratio is 0.2 for the oil displacement, and miscible displacement of formation water has a viscosity ratio of 0.13. So it's much more stable than the CO2 case. And after water flooding for 5 years, the CO2 is injected, but rapidly breaks through the fracture network. And after breakthrough, the displacement became very inefficient, and you see near the ceiling accumulation of CO2. And the formate case is much more stable to displace oil and water. So after breakthrough, it continued to displace the oil and the water. And you see there's no carbon accumulation near the ceiling because of the density of the injectant. So that insensitivity of displacement efficiency to breakthrough time is a significant advantage of formate over CO2 because that mitigates the risk of subsurface uncertainty. So this is summary result. Left-hand side, you see oil recovery, and the right-hand side, you see carbon storage for the two cases. And the CO2 case rapidly levels off after breakthrough. And the formate case continued to increase oil production and the carbon storage after the breakthrough. So that's a good advantage over CO2. So we discussed that the formate can stabilize the displacement front that result in enhanced carbon storage while increasing oil production. Now, another point to be discussed is injectivity, because we are injecting carbon-bearing water, and injectivity of CO2 may be much greater. So we studied this paper by Varuri et al. 2021. So they studied 9 aquifer CCS projects, and out of 9, 7 cases had enough information for us to compare CO2 and the 30% formate solution in terms of carbon injectivity. So I'm listing their permeability, depth, pressure, wellhead pressure as reported in the paper for their CO2 CCS project. And on the rightmost 2 columns, you see CO2 density in different units. So this is CO2 density at bottom hole temperature pressure as reported in the paper. So you see they, out of 7 cases listed here, 6 cases has very high CO2 density. It's understandable because aquifer CCS is good for high pressure so that CO2 has high density. And the one exception is this Kedzin project, project 8. So this made the analysis very interesting. So we are going to compare the 2 cases, CO2 injection and 30 weight % formate solution injection for the same wellhead pressure for the 7 cases to see which one is resulting greater carbon injectivity. So here's the result. So vertical axis is molar injectivity of CO2, basically molar injection rate of CO2 divided by molar injection rate of carbon with a formate solution. So it's called a carbon injectivity ratio here. So meaning if this number, y-axis is below 1, then formate case result in greater carbon injection rate compared to CO2. And the horizontal axis is the CO2 density at the bottom hole conditions, and 6 cases here, right, have a high CO2 density, therefore CO2 is more favorable, advantageous over formate in terms of carbon injection rate. But this Kedzin project result in the formate case being more favorable. So our analysis indicates that important factor is this bottom hole temperature pressure. So we increased the wellhead pressure for the Kedzin project from original 5 megapascal to the hypothetical wellhead pressure of 10 megapascal to see what happens to the carbon injectivity ratio. And we confirmed it actually increased carbon injectivity ratio to 8 from the original 0.5. So our current understanding is that formate case resulting greater carbon injection rate when CO2 density at the bottom condition is below 400 kilogram per cubic meter. And I'm showing the same result in terms of pressure, temperature, CO2 molar density plot here. So our understanding is basically shown here. So below this blue line, the temperature pressure condition shown below blue line. So this is a region where formate is more advantageous over CO2 in terms of carbon injection rate. And also this domain corresponds to the region where formate results in greater carbon density than CO2. So that indicates the best condition for CO2 injection and best condition for formate injection are different. So they don't compete for the same location. So that opened up a new opportunity of carbon storage locations. So this is the last slide. The formate, we presented the formate as a new carbon carrier that is highly soluble in water, brine, and that can contain the high carbon density even at the low pressure. And it viscosifies the solution, and we confirmed with turbidity alternation with carbonate. And the formate solution is a promising carbon carrier for enhanced carbon storage and the EOR, primarily because it stabilizes the front of displacement. And the formate is advantageous over CO2 in terms of carbon density and the carbon injection rate at the conditions below which CO2 density is less than 9 mole per liter. So with that, I would like to thank sponsors of a consortium and also collaborators, including Saskatchewan Research Council and OCOChem. And with that, thank you so much for your attention, and I'd be glad to answer any question you may have.
Thank you, Ryosuke. A couple of questions here. Zhang Wang, since FM solution is injected instead of pure FM, does it still have a richer carbon density over CO2?
Right. Yeah, formate is in the solution.
Yeah, yes, in the
Yes.
solution.
Yeah, so it's an ion. So,
Okay.
so yeah.
Okay. Yes, Hadi.
Yes, thanks a lot. That was very, very interesting. How would this hydrogen carrier would compare with piping and other liquid hydrogen, for example, transportation? What's the scale of it? When is it economic to go this way?
Oh, I see. Yeah, that's a great question. Yeah. So we really want to do economic analysis of that value chain. So the key idea is, so we are ultimately looking at green hydrogen. And instead of splitting water, our hypothesis is that overall, if we make formic acid and then transport, store, delivery using this liquid form of carbon carrier, perhaps that might be more advantageous over using hydrogen gas all the way from water splitting, transport, right? So we wouldn't see hydrogen until the delivery point that way, because proton taken from water is in the form of formic acid, and we don't see hydrogen gas until the delivery point. So.
And the transportation would be convenient in this form.
Yes, it's a
that would be
liquid.
the same as liquid organic hydrogen carriers. It's different.
This is a aqueous system, so it's not the same as other solvent type.
Excellent.
Hydrogen.
Thanks a lot.
Yeah,
Thank you very much.
But it's still hypothetical, so we want to study economics of it. Yeah.
Thanks.
Yeah. Thank you.
Great. I have a question myself. You use endpoint saturation as well as viscosity to adjust the mobility for your modeling anyway. So in terms of additional parameters that you may need to do some lab studies on, what may they be?
Yes, that's a great question. So we are exploring many parameters of this high concentration formate solution, viscosity, IFT, at a wider range of temperatures and solubility, and once we find good correlations, I think simulation is, I believe it's much more straightforward than experiment
Okay,
after getting physical properties.
great. Certainly with the support of UT Austin's computer programs, you can easily build that in once you get the lab work done.
Yes.
So second stage would be then, are you planning any pilots? And if so, when do you think you can get a pilot going?
Right. Yeah. So we are discussing a pilot test with several companies, and perhaps the first step is to see the long-term stability of formate by just using a single well. So it's like a single well tracer test, but that way we can confirm the formate long-term stability in actual subsurface conditions, and that's the current plan.
Okay. Any further questions? If not, anyway, it sounds really promising in terms of the density and the recovery, both on EOR and carbon storage. Once again, thank you so much for your
Thank you so
presentation.
much.
Okay.